Before I get started, I just want to say that this video is really intended for someone who is just getting started with electronics. If you already know what KVL, KCL, and Ohm's law are, then you can probably just skip to the next video in my series. That being said, I wanted to start by showing a schematic of the circuit we're going to build and the actual construction of the basic circuit, then we'll jump into the theory. Don't worry too much if I say something you don't completely understand at the start, because I plan to come back to these topics throughout the video. By the end of this video, I expect that you'll know a bit about voltage, current, resistors, wires, switches, diodes, and light-emitting diodes, which actually covers a large portion of what you need to know about hobbyist electronics, so let's get started. This is a schematic representation of the circuit we'll be building and analyzing. In my circuit, I have a 9-volt battery on the left. This symbol is specific to batteries, but just represents an ideal DC voltage source. The 9 indicates that this is a 9-volt battery. At the top is a switch, and on the right we have a resistor on top and a light-emitting diode on the bottom. Connecting each component are ideal wires. When the switch is open like it is now, no current will flow through the circuit. This is because there is no path for current to flow, and this is shown by the gap in the switch. Even with no current flowing, there are still voltages present in the circuit. The battery supplies 9 volts, and all of that will be dropped across the switch. With no current flowing, there's no voltage across the resistor or diode. Once the switch is closed, it becomes a short circuit and allows current to flow through the loop. I marked this as 10 milliamps, which is approximate, but we won't get to how to calculate that just yet. Just know that the current is the same in all the components in the entire loop because there's only one way for it to flow. With the switch closed, there's no voltage across the switch now because it's acting just like a wire, a short circuit. Now we have current flowing through both our resistor and our diode, so they'll both drop voltages. The diode will have about 3.1 volts because it's turned on, and the resistor will have the remainder of the 9 volts from the battery across it. Don't worry if you're lost at this point. I'm going to discuss the meanings of basically everything I've said in detail. But first, let's get a quick look at one way to build this circuit in the real world. These are the components I'm going to use for my example circuit. I have a 9-volt battery connector on the right, and going around clockwise, there's a white LED, a resistor, and a switch. The switch is not the type you'd usually use for this type of project, but it's just what I had on hand as an example. I'll set up the components in the same order we've already seen in the schematic. Technically, they can go in any order. As long as you get the polarity of the LED correct and they're all in series, the circuit will still work. Series means that they all connect end to end, so the current has to flow through all of them before returning to the battery. I'll use some wire that I pulled out of some spare Cat6 network cable. It's solid core and easy to work with for little projects like this. I chose not to solder any of these connections just to show that it can be done. It's better to solder your joints for electrical connectivity and physical strength. However, I can say that twisting wires together and some electrical tape can work pretty well in many circumstances. Through-hole LEDs will typically have one leg longer than the other. The long leg is usually the positive side or the anode. I like to double check this just because it doesn't take any time really, and I've run into parts before that didn't follow this convention. I chose to connect the resistor to both of the right-hand terminals on my switch just because this was easier than trying to connect it only to the center conductor. Since we're using the switch just for an on-off in this simple circuit, the third terminal can be shorted out without any problems. Keep an eye out for wires that might short the battery. Here I have 2 bare wires that are about the same length and could easily bump together if I move them around. A little bit of electrical tape on just one will prevent any shorts. If I were to wire this up more permanently, I would add some insulation to any joint that can move around freely. As you can see, the LED lights up when the battery is connected, and when the switch is turned off, then the LED turns off. It's a very simple circuit, but extremely useful as you move forward with electronics. Let's take a look at some of the theory behind this. Now that you've seen how easy it is to put together this circuit, let's talk about how it works. If you could look inside one of the wires to see the electrons, you'd see that they are physically moving. There's a great video from Electroboom explaining some details about this that I'll link in the description if you want to know more. This movement of electrons is called current. In the traditional model, electrical current actually measures the movement of positive charge, which is just the exact opposite polarity and direction to the movement of electrons. Even though the positive charges aren't really moving, they appear to in the same way that the world seems to move backwards when you look out the window of a moving car. Inside of any conductor, there are many free electrons that can move around if an electric field is applied to them. In other words, electricity can flow through conductors. A current source is an idealized circuit component we use for analysis that forces current in a circuit branch to a specific value. In this example schematic, the current source on the left is forcing 1 amp of current through the loop. As long as there is only one branch for the current to flow through, the current will be the same at all points. If we add another path for current to flow through, it makes things a little more complicated. Now we still have 1 amp of current flowing into and out of the current source on the left-hand branch. However, now we have 2 possible paths for the current to flow through, and we can't be certain of where the current goes. It could split half and half, or it might all go through one side. It will depend on our actual circuit. One of the fundamental rules of electronics explains how this split in current works, and that rule is called Kirchhoff's current law, often referred to as KCL. The rule states that you can sum all of the currents into any node and they will add up to 0. If a current is flowing out of the node, just give it a negative sign in your summation equation. In this case, we can definitively say that IA plus IB is equal to 1 amp, but we don't have enough information to solve for these 2 variables. I think that voltage is a little bit more of a nebulous concept to people when compared to current, so it's a bit harder to explain for me. The technical explanation is that a voltage is a difference in electrical potential between 2 points in a circuit. This is similar to how a ball placed at 2 different heights on a hill will be going different speeds when it reaches the bottom. One way I like to describe voltage is that it's how much the electricity wants to flow. On the left is an ideal voltage source symbol, and it indicates that there is a defined voltage between the top and bottom of the symbol. Let's give that a number for easy reference. It doesn't matter where you measure in this circuit, there will always be 5 volts between the top and bottom wires. If you have a conductor and you apply a voltage across it, you will get some current flowing through it. However, in the circuit shown, we have an open circuit, so there's no current flowing. One important thing to note is that voltages are always measured between 2 points, and polarity matters. For example, if you tried to measure a voltage on only the top wire, you would find that the voltage is 0. Even though that wire is at a higher potential than the other wire in the circuit by 5 volts, that's constant along the entire wire, so the difference in potential between these 2 points is 0. Another way to think of it would be to go back to our balls rolling down a ramp example. In this case, the ball would be placed at an elevation equal to 5 volts, but the bottom of the ramp is also placed at 5 volts, so there's no slope for the ball to roll down. It's very common for engineers to refer to a voltage at a particular point in a circuit without giving a specific reference. For example, the voltage at the top wire here would be commonly called positive 5 volts. This is always done with an implied reference point, typically a node defined as ground. This symbol on the left is the most commonly used for ground, but there are others. Just remember that voltage is always between 2 points, and if the second point isn't defined, generally speaking, that second point is the ground node for the circuit. Another fundamental rule of electronics is called Kirchhoff's voltage law, or KVL, and it states that all of the voltages in a loop will add up to 0. In order to make this loop, you need to choose any point on the circuit and trace a path from that point back to itself and sum up every voltage along the way. Be sure to include polarity in your summation. I like to use the rule that as I cross a voltage, if I trace from minus to plus, that's an increase in voltage and thus a positive value in my equation. If I cross plus then minus, that's a reduction in voltage and thus a negative value in my equation. Using this rule, we can determine the unknown voltage at the right side of this circuit. I'll choose to start at the bottom left of the circuit as my starting reference point. Tracing clockwise, I first encounter a negative to positive polarity 5 volts, which I denote as plus 5 volts. Then I encounter 2 plus to minus voltage sources that I denote as minus 1 volts and minus 2 volts respectively. And finally, I mark the unknown voltage as minus Vx because the polarity is assumed as plus to minus. Across the bottom, there aren't any more voltage changes, so that's it for my equation. I can easily move Vx to the other side and then solve, and I get Vx is equal to 2 volts. To me, Kirchhoff's voltage law is much less intuitive than Kirchhoff's current law. The way I like to think about KVL goes back to the balls rolling down a hill and their potential energies. The potential energy of an object on a hill is directly related to its height. If you're standing on a hill, it doesn't matter where you start, but if you walk around the hill going up and down, each up and each down being representative of a voltage change, then you make it all the way around the hill and back to exactly where you started, then all of your ups and downs must add up to 0. Otherwise, you'd have finished at a different height, and thus a different potential. To make your loop complete, you have to get back to the exact same potential you started at. I wanted to show these two special cases here. You can't have a constant current source hooked up to an open circuit, and you can't have a constant voltage source hooked up to a short circuit. They both result in infinite values and can't be replicated in the real world. Similarly, you can't have two current sources in series or two voltage sources in parallel. These would result in the circuits being overdefined. Most simulators would just give you an error. Now let's look at our first component, the resistor. The US symbol for a resistor is shown on the right. It will usually have a value of resistance next to it in a circuit diagram measured in ohms. To understand a component, we need to know the voltage-current relationship for that component. For a resistor, this is just a simple linear relationship. If a voltage is applied across a resistor, it will produce a current proportional to the applied voltage. Note that the current passes from plus to minus, which is a reduction in voltage, also called a voltage drop. Resistors will always have this polarity. If you solve a circuit and find that you get a negative voltage or current value on a resistor, then it just means that you assumed the polarity incorrectly. Ohm's law mathematically describes this very concisely. The most common form of Ohm's law is V equals I times R. This is an extremely important relationship to know if you're going to do anything with electronics. There are also two other forms of this equation, but they can all be found through simple algebraic manipulation of this basic form. The second form is useful if you're given voltage and resistance and want to know current. The last form is useful if you know the voltage and current and want to know resistance. This last form is the one we will use to calculate our desired resistor value for our LED circuit. To show an example, if 5 volts is applied to a 10 ohm resistor, then we can calculate the current in the circuit with Ohm's law. Using the second form of I equals V over R, we quickly get that the current is half an amp. I particularly like this method of remembering Ohm's law. If you draw the equation this way, all you have to do is cover up the value you want, and you can see the equation for the value you need. Covering V gives you I times R. Covering I gives you V over R. And covering R gives you V over I. Moving on to the most complex component in our circuit, let's look at the diode. On the right-hand side of the screen is the symbol for a diode. Adding 2 arrows is a common way to indicate that a diode is a light-emitting diode, or LED. This is a semiconductor device, so its voltage-current relationship is nonlinear. I'm not going to go into details on exactly how these work. That would go well beyond the scope of this video. However, I will explain how to use one and what to expect from them. Note that diodes have a polarity to them. The triangular side is the positive side, also called the anode, and the side with a line is the negative side, or the cathode. When you apply a negative voltage across a diode, that is to say that you reverse bias the diode, then the diode will be in the off state, and it will not allow current to flow through it. If you apply a small positive voltage, the diode will still not turn on and current will still not flow through it. This is because diodes require a minimum forward bias voltage before they will turn on and allow current to flow. Once the turn-on voltage is reached, however, the diode will act similarly to a voltage source and will allow a great deal of current to flow through it without much change in its forward voltage drop. Let's look at a simulated example to understand this better. The symbol indicates that this is a function generator and not just a DC voltage source. The Y-shaped symbols on either end of the circuit are just voltage measurement points. Reference to the ground symbol at the bottom. These three symbols are just references for the simulator and don't affect the circuit. The arrow in line with the resistor is a current meter, which acts like a wire and also does not affect the circuit. Running the simulation, you can see the input voltage, LED current, and LED voltage as they relate over time. The input voltage slowly ramps up from -5 volts to +5 volts, which is what I programmed it to do. The second and third graphs show the current and voltage of the LED respectively. Before this point, at about 6.25 seconds, the LED current is 0 and the voltage across the LED is equal to the input voltage. This is because the LED is blocking current from flowing. So the current through the resistor is also 0, and the voltage across the resistor is defined by Ohm's law as current times resistance. 0 times 1000 is 0, so the voltage drop across the resistor is also 0. Using KVL, this means that the voltage across the LED must be the remaining value, which is the entire supply voltage. Once the LED's turn-on voltage is reached, the diode will act like a voltage source. On the right, you can see that the LED voltage on the bottom remains relatively constant after current starts flowing through the LED. The LED current is directly controlled by the resistor here because now the voltage across the resistor is non-zero. You can solve for the resistor voltage using KVL as shown here. As Vn increases, the LED voltage, Vf, remains constant, and thus the resistor voltage increases with the supply. Using Ohm's law, we can calculate the current through the LED for a given resistor voltage. As the voltage across the resistor increases, so does the generated current through the resistor, and thus the current through the LED. Now you have all the basic tools you need to design a simple LED circuit, so let's go ahead and design one. First, we need a voltage source large enough to turn on our LED. This is the reason that I've selected a 9-volt battery for this version of the circuit. It's just the easiest way to get enough voltage reliably and easily. A real 9-volt battery will have a voltage somewhere between 9.7 volts and 5 volts, depending on how new it is and a bit on the manufacturer. This graph shows two discharge curves from a Duracell Ultra 9-volt battery's datasheet. One for a 2 mA load and one for a 10 mA load. You can see that when the battery is new, it can have up to 9.7 volts of output voltage. And as it gets used up, the voltage will drop down to about 5 volts. You don't need to design your circuit to work across this whole range, but it's best to in order to maximize the use of the battery's power. The LED I've selected is a through-hole white LED from Cree, which just so happened to be in stock and the lowest price on Mouser when I checked. You can do this with pretty much any LED, so don't go out and order LEDs if you have some laying around. You just need it to be bright enough to light up your intended area. Sometimes that'll mean using more than one. The important specs from the datasheet are the forward voltage, the test current, and the absolute maximum current rating. In this one, we can see that the desired operating current is 20 milliamps with a forward voltage typically of 3.2 volts. But it could be up to 4 volts. We also see that we should never exceed 25 milliamps or the device could be damaged. The datasheet also provides a luminous intensity versus forward current graph, which shows us a couple of interesting things. First, they tested the device way beyond the rated absolute maximum. So the LED will probably work fine with higher than 25 milliamps of current, but it will likely cause it to wear out faster. Also, the difference in brightness between the test current of 20 milliamps and half of that at 10 milliamps is about 50%. This is probably still bright enough for our application, so just keep in mind that you want to operate the LED somewhere between these two. Other LEDs will have different plots, and I'd recommend to check those out so that you can get an idea of how the LED will behave. Now that we've selected a power source and an LED, we can determine what resistor value to use. This is done using Kirchhoff's voltage law, Ohm's law, and all the values we already know. I start here and add up the voltages around the circuit. Vn is from minus to plus, so that's a voltage gain, and positive in our equation. Vr is plus to minus, so that's a voltage drop, and it's negative in our equation. Vf is also plus to minus, and so it's a voltage drop. If you wonder how I know the voltage polarity on the resistor, it's just an educated guess. You could also solve this with the opposite voltage polarity and you'd just end up with negative answers, indicating that your polarity was flipped. Once we have the KVL equation, we can solve for the resistor voltage. I know that my battery can be as high as 9.5 volts and as low as 5 volts, and that my LED is typically 3.2 volts, but it can be up to 4 volts. Using these two ranges, I can get the minimum and maximum resistor voltages. I'm going to use this form of Ohm's law because I know voltage, which we just calculated, and current, which is given to us in the LED datasheet as 20 milliamps. Solving both sides gives R1 is 315 ohms and R2 is 50 ohms. So which value do we use? Let's look at what happens in each case. Please note that I'm simulating with a different LED, but it's very similar to what we're using, so our current calculation should be pretty close. I just want to show how the current changes as the supply decreases over time and how the resistor value affects this. Using a 315 ohm resistor, I ran a simulation with the supply voltage decreasing from 9.5 to 5 volts, and you can see the results here. The LED current starts at about 20 milliamps like we wanted, but it eventually reduces to only 6.3 milliamps. This would still be enough current to light up the LED, but it would be about 25% brightness. I should mention that this might be bright enough for our application still, but it would be noticeably dimmer than with a full battery. Switching to a 50 ohm resistor, the current at full voltage is much higher, well beyond the absolute maximum rating of 25 milliamps in the datasheet. It eventually gets down to about 20 milliamps, but this is definitely not the solution we want. I wouldn't ever want to run a device beyond the absolute maximum ratings in the datasheet. What we can do in this situation is adjust our current requirement at the full voltage to be a bit higher than what we want, and then see how long we can stay above 20 milliamps. Again, we're using Ohm's law. With our new current at the maximum voltage value, we get a resistance of 252 ohms. This will give us exactly 25 milliamps when the LED is operating normally with a full battery. Let's see what the resistor voltage is when the current is 15 milliamps, which should give us about 75% brightness. We just use another form of Ohm's law to get the voltage across the resistor as 3.78 volts. After that, recall that the voltage across the resistor is just the battery voltage minus the diode forward voltage. Rearranging this, you get that the input voltage is the sum of the resistor voltage and the diode forward voltage, and that gives us about 7 volts. Looking back at our battery discharge curves, we can see that 7 volts will give us the majority of the lifetime of the battery, so this isn't really a problem. Also, the LED will continue to be lit even with lower voltages, but it just won't be as bright. The last thing we want to know is how much power this resistor needs to dissipate. This is a critical step that's often ignored. Make sure to get a resistor that can handle the power, or you might end up making a fire starter instead of a light. Power is just current times voltage. We know that voltage is current times resistance in a resistor from Ohm's law, so the power can be written as P equals I squared R. Solving with our values, we see that the resistor needs to dissipate about 158 milliwatts. This means that we can use a standard quarter-watt resistor. At this point, you've got a finalized design for your circuit. The only thing you really had to calculate was the resistor value. Now all that's left is to choose exactly what components we'll be using. We've already got our battery and LED selected, but we need to get our switch and resistor. If you only want to use one LED, this is the circuit you use. However, if you decide that you need more than one LED, then you can add those in parallel with what we already have. Just be sure that the switch is in series with all of the devices, and that there's a resistor in series with each diode separately. It could be tempting to put only one resistor in series and then have the diodes in parallel. However, there are problems with that. The diodes don't have exactly the same forward voltage and the current won't split evenly. I would highly recommend against doing that. Just use one resistor per LED and you'll be fine. Let's go to Mouser's website and take a look at how I select my components. Before I start, I'd like to say that I'm not sponsored or otherwise financially motivated to use Mouser over other distributors. They just happen to be geographically close to me, and I've been using them for a long time without any issues. Now let's find some components. I want to start with the resistor because that'll be fairly easy. Resistors are found under passive components on sites like this. So the resistance that we need is 252 ohms. So I'm going to go ahead and just take a look and see if that number specifically is available. Looks like it is. We do see an axial termination over here, so let's check that one. It looks like they do make a resistor that's 252 ohms. However, it's not in stock at Mouser. So let's go ahead and get something that's close to what we need. Now I'm going to keep 252 selected. just so I have a reference point. But then I'm going to select all the way down to 330 because I know that's a common value. Now that leaves us with quite a few devices available. I'm going to go ahead and sort them to the axial devices because for this particular project, we want it to be something easier to work with. I'd like to have at least a 1/4 watt, so let's go ahead and do up to 500 milliwatts. And I'm going to first sort by the resistance to see, because I set the bottom at 252 and then I went up from there. I chose not to go down from 252 because that would increase the amount of current going through our diode, and we don't want to do that. If you remember what we did with our 50 ohm resistor earlier, that gets well over the absolute maximum rating of the device. So 252 is where we're sitting right at the abs max when our battery's fully charged. Now looking, we see that our 252 ohm resistor is still there, the one that wasn't in stock. However, there is a 255 ohm resistor that is in stock. He's 17 cents, and you get some bulk discounts here. You can look a little bit further down. There's another 255 ohm resistor, still a 1/4 watt, and this one is much cheaper. You can get 100 at 3 cents a piece. So this is what I would choose to do. Going to the All Products page, we can find our switches. You just look down through here and find electromechanical. And then what we want specifically is switches. And the type of switch, it's called a basic or snap action switches. These are the type of switches that are like push buttons. Whenever you press it, it does something. The specific type that I want is a roller lever actuated switch. And you can see that these can be fairly expensive. We've got $6 for one switch here with the first one. But this one will show you basically what a roller lever switch is. There's the actual switch is underneath this metal bar. So whenever you press on this rounded end, that's going to actuate the switch and cause the center pin to be switched to one of the other 2 pins. Although you definitely have to check the data sheet. Sometimes it's not the center pin. It might be one of the 2 end pins that's common. We'll take a look at our data sheet when we pick our switch. Sort by price. Now looking at this, at the top, I don't know what this one is. This looks to be just the metallic part that's actually the rocker, not the actual switch itself. The first one that actually is a switch is this one, manufacturer part number, MS085, and so on. Now, I'd like to copy that number, but I'm not able to select here. It looks like they've disabled that on the website, but I can just right click, copy the link address, and grab it out of there. Let's take a look in this datasheet and try to figure out exactly which one of these switches we're looking at on Mouser right now. The first thing you'll notice is they have a part number breakdown here. So this is extremely useful. We have MS at the front, that's the series. And the operating temperature is 085, so we've got an 85C part. Then we've got 05, which means it's a 5 amp switch. And we have 05 again, that's our actuator. F050 is our operating force. And C1 is our termination. And A is the circuit. A means single pole double throw, which is great. That means it's got a common connection, and then it's going to have 2 pins that common connection switches in between. So let's go ahead and take a look down here. We have the actuator type of 05. So 05, it has a roller lever. So this one actually has the roller ball on it. And I really like these. They generally are more expensive though than the roller levers here, where they have this piece of metal that's just rounded on the end. But this would work perfectly for my application. We saw that C1 was the connection type. So C1 has these longer tabs coming out the bottom, which means it's going to be even easier to wire up than the S1 version. I was looking at one of these S1s earlier. So going back to the beginning, we can take a look at the actual circuit here. So it looks like these all work exactly the same way. We have pin 1, then 3, then 2. A very strange numbering scheme, but hey, I'm not going to complain. It's clear at least. Pin 1 is common. So common is actually on the end over here, which I've found to be not that abnormal on these types of switches. A lot of switches will have the common pin in the middle. So, but yeah, pin 1 is our common pin, and then normally connected NC is pin 2. So whenever you're not doing anything to the switch, pin 2 is what you're going to be connecting pin 1 to. And then pin 3 is the normally open. So now, if you think about this, whenever you're connecting a switch that's controlling a light inside of a cabinet, when the cabinet is closed, it's going to be pressing this in. When it's pressing that in, it's disconnecting the normally closed, and that means the light's off. You definitely want your light connected to normally closed instead of normally open, which is kind of backwards from the way you'd usually hook up a switch. Because typically when you press a switch, you want to have something happen when you press it, not when you release it. But in our case, this is exactly what we want. So this is a good switch. That's what I would choose. So I would go ahead and buy a few of those. Because these are a little more expensive than resistors, I would typically only buy 2, maybe 3, just so I would have spares. But I wouldn't want to just buy a whole bunch of them. You're not going to get a great bulk discount on this type of thing. The last thing we need for our project is the power connector, which we're going to be using a 9-volt battery. So let's go into power here under battery holders, clips, and contacts. They have a section for 9-volt battery snaps and contacts. And I'm going to select one battery here, and then I'll sort by price. Just looking down the left side, the first one that is exactly what I want is this one. That's just the normal connector for the 9-volt with some wires hanging off the end of it. Data sheet for this is really simple, just has a red and black wire. Red goes to positive, black goes to negative, and that's it. There are other options available. For example, the ones that have like a plastic housing are a little bit more sturdy. They're not a whole lot more expensive either, so you might choose to go with something like that. Really, all that matters is you can connect your batteries up. That's all there is to it for this version of the project. In my next video, we'll be looking at the more advanced version of this project. Thanks for watching. If you have any questions, please post them down in the comments. Have a great day.